Okay, well, let's get started. It's time. So, last time we finished talking about the basic form of SVM, the support vector machine, right? And again, the purpose of the support vector machine is to find a line that separates those points the best, yeah? And we define best as having the maximum margin, yeah? The distance from those points should be the biggest, yeah? You have the biggest cushion to defend against any potential noise or errors, yeah? So that's the purpose of SVM. And then after some algebraic manipulation, eventually we get to this form, right? Maximizing the margin after some normalization becomes minimizing this W transpose times W. Yeah? Remember, our W is unaugmented. Yeah? We do not augment our W. Okay? So turns out maximizing the margin gives you minimizing this product as the objective. At the same time, we want to satisfy this constraint. This constraint basically is the separation of the points. Yeah? And after normalization is greater than or equal to 1 has a special meaning, right? If it's exactly equal to 1, then your particular data point N sits right on top of the boundary of the margin, right? And for most points, at the end, you will have the product to be strictly greater than 1. That means it is those points, they are away from the margin, yeah? Like this one, this point here, okay? But then the points that are exactly equal to 1, they just sit right on top of this boundary of the margin, okay? So that's the our current understanding of the SVM so far, okay? And these points, in an informal way, we say that the points that sit right on top of the boundary of the margin, they are called support vectors. In the sense that they support this boundary. Yeah, it holds the boundary in place, holds the entire margin in place. Yeah, they are the so-called support vectors. And there's a optional side information that says, well, if you want to know how well your line works during testing, okay, that testing error turns out to be upper bounded by a function that is linearly increasing with the number of support vectors. So in other words, the fewer support vectors, the better. Okay, so but this is optional. Yeah? It's in the textbook. But then the natural question would be, well, in general, how can I find these support vectors, and how many support vectors do we have given a data set? Yeah, after I solve the SVM. So that question can be answered by looking at the Lagrange dual domain of this problem. Okay, and that's what we're going to study today. And the Lagrange dual form of this problem turns out give us more than telling us how many support vectors we have. More importantly, which we'll discuss next time, is that the Lagrange dual form can allow us to produce SVM for nonlinear boundaries. Yeah? So far, we only studied linear boundaries, right? To go to nonlinear boundary, it turns out that the Lagrange dual form is the key to that. Yeah? So first of all, but today we only concern ourselves with one question, which is how to identify the support vectors. And one reason we want to identify, as I said, is to know how well this support vector machine will work when you go to testing. And the method to go forward is the so-called Lagrange duality or Lagrange dual formulation, DUAL. Kind of dual, this means that a equivalent form is another form. And then next time we'll talk about how to use the dual formulation to handle nonlinear transformation with SVM. So for now, what is the Lagrange do? Yeah, Lagrange is Dr. Lagrange is somebody. I believe it's the 19th century, 18 something. I forget exactly but long time ago. Yeah, it's a way to solve optimization problems. So to introduce the Lagrange dual formulation, we first have to introduce what's called the Lagrange function. It's also called the Lagrangian in many textbooks. The Lagrange function, we denote it by a scripted L like this. It is a function of the original variables, W and B, plus another set of variables, alpha, called the Lagrange multipliers. Okay. Oh, I forgot to mention that because we have the dual formulation, then the original formulation of SVM, that formulation with constraints, is called the primal problem. Yeah, so as opposed to the dual problem later. Okay, so this original form we will call it the primal problem. So this Lagrange function is defined very similar to the original optimization problem. If you look at the original primal problem, we have the objective, then we have the constraint. Okay. The purpose of the Lagrange function is to combine the constraint and the objective together. Okay? So instead of saying that I have to limit ourselves to always have this product greater than or equal to 1, we allow some violation of this constraint. Okay? However, if you violate the constraint, I'm going to assign a penalty to it. And I'm going to add a penalty to your objective. Okay? So therefore, now this would be of this form. First, the original objective, right? And then we have the penalty for constraint violation, which looks like this. Alpha n multiplying our constraint, which is yn, w transpose xn plus b, right? It has to be greater than 1, so now we subtract 1 from it. Okay? Again, if you compare the original formulation, the primal formulation with the constraint, it says that every one of them has to be greater than 1, right? So what happens if we don't satisfy the constraint? We have something that's less than 1. What happens? Then this thing will be negative, right? If this product is less than 1, this is negative. But then there's a minus sign in front here, yeah? So therefore, we have a positive penalty here, yeah? If you violate the constraint, we're adding a positive term, which is a penalty to this objective. Okay? Initially, you want to minimize this, right? Now we're adding something to it. Yeah, it's a penalty to your original objective. So this is the penalty for constraint violation. Okay. So therefore, the Lagrange function, the Lagrangian, it is a penalized version of the original objective. Okay, everyone okay with that? Yeah? So this is one way to kind of give a soft constraint, right? We have seen this before. Sometimes we have a hard constraint, but then now we say, well, yeah, maybe I allow you to violate the constraint, but then there will be a penalty for it. Yeah, there will be a cost. So now, for this to be penalty, of course, this alpha n, these so-called Lagrange multipliers, have to be non-negative. Yeah, it's a kind of a price that you pay for the amount of violation that you have. Yeah, so alpha 1, alpha 2, these are the newly introduced variables. Right? They have to be non-negative, and they are called either the dual variables or the Lagrange multipliers. Multipliers. Okay. So the reason that we want to introduce the Lagrange function is that it turns out that if you solve this optimization problem using the Lagrange function in a specific max-mean form, we can actually solve the original problem. Okay? It turns out this soft constraint form can still allow you to solve the original problem with hard constraints. Okay? And that was developed by Lagrange, of course. Yeah, that's why this method carried his name. Yeah. So we're just going to state this as a fact without proof. There are some mathematical proof behind this fact. Okay, but we won't deal with it in this course. So basically, says that if the primal problem is convex, which our problem is, yeah. Remember our primal problem, the SVM problem we have shown last week, that it is a convex problem. In fact, it's a convex quadratic programming problem. Yeah, so certainly it's convex. And in general, for any convex problems under mild conditions, this Lagrange method works. Yeah, so I'll describe that Lagrange method right away. So for primal problems that are convex, for a primal problem that is convex, let's say. Under mild conditions, again, we're not going to describe the mild conditions because we're not going to go to the mathematical details. Yeah. So say that we have the following so-called strong duality theorem or strong duality property. Basically says that the primal problem and the dual problem are the same. It says that if we want to get the optimal solution to the original problem, to the primal problem, it's the same as doing the following two-step process. We well, let me just write this, two steps. We first minimize this Lagrange function, but only over W and B, yeah, the original primal variables. After that, we maximize it over the remaining variable, which is alpha n. But then, of course, they have to be greater than equal to 0 as required. Yeah. Okay. So you see, there's a max-min problem over the Lagrange function. Yeah. Turns out that you do this two-step optimization at the end. The solution that you get for the optimal W and B are these optimal solutions to the original primal problem. Okay? Again, just take this as a fact. There is a proof for this. You will see this proof if you take a graduate course on convex optimization, which we offer in this department. Okay? But we're not going to go into that proof here. Yeah. So just notice the two steps, right? First, you minimize the Lagrange function, but only over W and B. So you take the alpha as constant in the first step. Yeah? So therefore, after you optimize this, you get a function that is a function of alpha. Yeah? And then you maximize that function of alpha over alpha. Yeah? So that's the second step. Okay? That's what the Lagrange method does. Yeah? Two-step method. And then at the end, we can find the optimal solution, turns out. Well, again, under mild conditions, which we don't have to worry too much about. Yeah? So let's take a look at these two steps, what these two steps give us for the SVM problem. Yeah? So first, we have to solve the minimization problem over W and B. Yeah? We want to minimize L, W, and B when alpha is taken as a constant. Yeah, so this is with respect to, WRT stands for with respect to. Yeah, it's a very common notation. Yeah, only these two variables. Yeah, again, at this stage, we just treat alpha as a constant. Yeah. This is a unconstrained optimization now, right? There's no constraint anymore. Yeah, just minimizing that Lagrange function. Yeah, no constraint because we already moved the constraint into the objective now, right? Yeah, as penalty. So therefore, to minimize this, how do we do it? We have done this many times by now, right? We take the gradient, set it to 0, yeah? And because this is convex, setting the gradient to 0, you get the optimal solution, yeah? So the gradient of this function set to 0, right? That's what we want to do, right? So what does it give us? Well, what is the gradient with respect to W? Well, let's screw up a little bit. Let's look at our Lagrange function again, right? On top there, that's our Lagrange function, taking the gradient with respect to W. By now, everyone should be able to do this quickly, right? First term is a square term, so you just get W, yeah? And then the second term is a linear term, yeah? So just take the coefficient in front of W, yeah? So this is easy to do. So the first one, we get W because we have 2W, but then we have half in front, yeah? And then n equal to 1 to n, because the coefficient in front is simply alpha n, yn, and then xn, I believe. Transpose, no transpose, yeah? Just like that, is equal to 0. Right? So easily, W simply equals to summation n equal to 1 to n, yn, xn, like that. Yeah? So that's the optimal W to minimize the Lagrange function. And then we take the gradient with respect to b, but then it's scalar b, right? That means just taking the partial derivative with respect to b, yeah, equal to 0. What does this give us? Well, what kind of function of b is this Lagrange function? Well, if we go back, that's Lagrange function. Only one term involves b, right? It is a linear, just something multiplying b. You just take the factor outside, yeah? So that says we have to have n equal to 1 to n, I think alpha n times yn times b, right? That one has to be equal to 0. Yeah? So that coefficient has to be equal to 0, right? So therefore, now we're all set, right? We have, even though this does not explicitly give us what optimal b is, at least we know what it should be, yeah? So what is the optimal L, WB alpha? Yeah, treating alpha as a constant for now, right? So first of all, let me just rewrite the form above, yeah, the function of Lagrange function. Right now, I'm not doing anything yet. I'm just writing it out, just copying from above, except that I'm going to break up the sum, yeah? There's a sum here between wx plus b, right? I'm going to just separate all these terms, just make things a bit easier to look at. And so I have summation n 1 to n, alpha n, yn, w transpose xn, and then I have minus n equals to 1 to n, alpha n, yn times b, plus, and then finally that plus 1 term, I get alpha n, like that, right? Okay, so far I'm not doing anything yet, right? I'm just breaking up that Lagrange function as defined, right? Nothing yet. But now I can substitute these optimal solutions, W and B here, inside this one, right? After I've taken the derivative to set to 0, yeah? So this one I know, yeah? If I can take this W outside, right? So whatever inside is simply W, the optimal W that we found, yeah? So therefore this one has to be W transpose W, right? And then, of course, they can merge together with this half together, yeah? How about the other term here? This thing is 0, right? When we optimize speed, this one has to be 0. So this one, of course, this one is equal to 0. And we can, this whole term goes away, right? Yeah? Furthermore, since I can combine these two together, I get negative half of W transpose W. And then I also know what W is. I can substitute those things into this W transpose W, right? So we also know that W transpose times W is equal to what? W transpose times this, what's that? Alpha n, yn, xn, like this, right? And, oh, I forgot it. And of course, this W transpose can also be written as a sum, but I have to use another dummy variable, m, yeah, ym, because eventually I'm going to merge these two sums together. Ym, xm, like that, right? Yeah? Everyone agrees? Yeah? For the optimal W, I just substitute this thing in there. Okay? So this is just a psi node, yeah? So therefore, after this, I can simplify the L function above, yeah, by substituting this block in there as minus half of W transpose W, right? So it's a minus half W transpose W, which is this. I can cross multiply the things inside the sum to get a double sum. Yeah. N goes from 1 to m goes from 1 to m. Yeah. And then alpha m, ym, yeah, xm transpose xm, right? And then plus the other last term, n equal to 1 to m, alpha m, like that. Okay? Yes, yeah, because the W, right? So basically, when I substitute those optimal W in there, that's what I get, right? Okay. Get this very nice, clean, somewhat clean form, yeah? Okay. Yes?
Sorry, I'm a bit confused. Is W the same as W transpose?
Oh, it doesn't matter because xm transpose times xn is the same as xn transpose times xm. Yeah. Anyways, these are dummy variables anyways. N and m dummy variables, I can swap them anyway. It doesn't really matter. Any way you look at it, they're the same. I understand your concern, but yeah, there's no problem. It's totally symmetrical, right? Okay? Yeah. The dimension is d-dimensional vector. The W is always d-dimensional, right? The same as our x, right? Yeah. Oh, I forgot the transpose here, of course. There's a transpose here, over there. Yeah, this I write it in red because I forgot about it here. Yeah, this is the transpose. Should be there, just to be, yeah, because W transpose. Okay. So what we have done here is that now we have finished optimizing this Lagrange function based on W and B, right? You see that the final form, this optimal form, does not contain W and B anymore, right? Because I already chosen optimal values. I've already put in the optimal values of W and B in here. Yeah? So this is purely a function of alpha now, right? Purely a function of alpha. So remember our Lagrange method, yeah? 2 steps, right? First, minimize that. And then with second step, then we maximize over alpha. So indeed, at the end, we have a function that's a function of alpha in order to maximize, yeah? So now we can go to the second step now. Everyone with me? So now I can go. Right. Here I'm going to let's just call this alpha, yeah, because I have already optimized W and B and substituted those optimal W and B in there. So right now only a function of alpha. So now the second step, that following the recipe of the Lagrange method, is to maximize this L of alpha, yeah, subject to, of course, alpha n is greater than equal to 0 for all n. Yeah. But also we have something else, because previously we never explicitly set up what B is. We still carry this condition that alpha n times alpha n times yn, the summing up over n should be equal to 0. Yeah, that is something that we have to satisfy from the previous step. So we have to carry this. So and also and this one, summation n goes from 1 to n. Alpha n, yn has to be equal to 0. Okay. That's the condition that we have to satisfy from before. And if you look at this, this is another optimization problem, right? Minimizing this new Lagrange function that is expressed only in terms of L, subject to these constraints. Okay? And this is called the dual problem, okay? And as opposed to the primal problem. Dual problem. Yeah. And Dr. Lagrange has proved many years ago that turns out that solving this dual problem is the same as solving the the primal problem. You recover the same solution in general. Yeah. Yeah. Yes. Yeah. That's right. So linear problem is a special case of a convex problem. Yeah. Very good. So now the question is, given that we accept the Lagrange theorem, yeah, to say that solving this is good, yeah, the question is, can we solve this? Is it easy to solve this problem in order to find our SVM solution? What do you think? Does this problem does it look like an easy problem to solve? Yeah, given that L of alpha is of the form over there, yeah, that we have derived. And then we have these constraints. These are linear constraints, obviously, right? Linear constraints, what kind of objectives do we have? Yeah? In terms of alpha, of course, yeah. In terms of alpha, what kind of objective is it? Exactly, yeah, very good. This is a quadratic form, right? Just the product of two things, okay? This is a quadratic function. You can actually write it out as the Q and times U and times P times U and so on. That canonical form of the quadratic programming problem that we discussed last week, okay? You can convert it. We're not going to do it. We'll skip those level of details. But all that we need to know is that this is, turns out, also in fact, convex. You can prove that it is convex. Quadratic programming problem. Quadratic program. Or quadratic programming problem, if you want. Yeah? So therefore, there are you can use pretty much any standard software solver to solve this kind of optimization problems. Yeah, and it will give you the optimal solution to this problem. Okay? There is no analytical solution, but then there is very efficient numerical solutions. Okay? And again, to prove this, you just have to match. Yeah, Q is equal to blah blah blah, P is equal to blah blah blah. You know, AM equal to blah blah blah. You know, those things that we did for the primal problem to show that it is quadratic programming. Yeah. So we're not going to do it. You can try to do this at home yourself if you want. If you want to cheat, you can always read the textbook. The textbook has all the exact answer for what this item should be. Yeah, you just convince yourself that it is quadratic programming problem and it can be solved. Yeah. Okay. So once you find this, that means that you can solve this problem to find optimal alpha. Now we have to discuss how do we go from the optimal alpha back to the optimal solution to the primal problem, the optimal W and B. That's what we want in the end, right? The optimal line, yeah, represented by optimal W and B. So how do we do it? So the next step is to recover or just to find the primal solution, to find optimal W and B after you found the optimal alpha. Okay. So we have to find two things, W and F, right? W and B, sorry, W and B. But W, we know, W is easy to find. Turns out if you remember what we had before, right? We say on top there, that says that W has to be of this form, the optimal W. Now we know what alpha is, the optimal alpha. Just substitute the optimal alpha in there, there you have it, yeah? The optimal W, yeah? And we know that that one would be optimal W because Lagrange told us so, and Lagrange had to prove that it is, yeah? So we have to trust that, and well, you can check the proof yourself. You don't have to trust it. You can check the proof, and then you will be convinced by the proof, and you know that that's optimal. So from the so-called a strong duality, we know that all that you need to do is to substitute duality. Yeah. We know that if alpha n, just say the entire vector, yeah, of Lagrange multipliers. This one is optimal. for the dual problem. Then we know that W of that form, n equals 1 to 1, alpha n star yn xn is optimal for the primal problem. Okay. Now the question is how to find B. Yeah. Now that's a bit challenging because we don't have a formula for B, right? The formula for B is implicit. Remember, yeah? When we set this partial derivative to 0, we get something like this. B goes away. So this is an implicit thing. So how do we find B? Okay. So it turns out that on the way to find B, which is somewhat more complicated than finding optimal W, we actually discover something even more interesting. Okay. So therefore, in fact, to finding optimal W and B and more over here. In the sense that it turns out that on our way to find B, we also discover how to find the support vectors for our support vector machine. Okay, so that's the second point. Okay. So on this point, first of all, we have to recognize that if we indeed solve the primal problem, that means all of the things that we do at the end, the penalty that we have added to the objective function before should be 0, yeah, right? Because the original objective does not have the penalty, right? So if we can claim that at the end we do solve the original problem, then the penalty must be 0, okay? And in fact, we have a theorem that says, yes, this does solve the original problem, yeah? So therefore, by implication, at the end, after we solve all of this, our penalty must be 0. Okay, is this logic clear? Yeah. So because we know for sure by the Lagrange theorem that solving this, by doing this, we actually solve the primal problem. That also implies that at the end, but when we substitute optimal things inside, the penalty must be 0. Yeah? Okay, so that's an important observation. So at optimum, the penalty that we previously added to the objective of the primal problem must be 0. Okay. Everyone with me? Everyone okay with this idea? And for those of you who are, well, let me write it down first, yeah, maybe. So in other words, the penalty, remember what we had, was alpha n star, right, a weighted amount. This is the price for the violation, and then times the violation amount, right? So this is the amount of violation, plus b minus 1, right? Previously we said that the constraint says that this thing has to be less than 1, yeah? So now take the difference, that's the amount of violation, and then there's a weight. The price of violation is the Lagrange multiplier, which is alpha m, the price of violation. This one has to be equal to 0 for all m, yeah? We cannot allow any violation at all for any data point, right? Otherwise, you will not be solving the original problem. Yeah, make sense? Yeah, we cannot allow any violation for any data point. Yeah. So this must be 0 because this is our penalty. Okay. In fact, this is called in the optimization literature. For those of you who maybe have heard about optimization or learned about optimization before, this is it is called a complementary slackness condition. Yeah? Complementary slackness condition. It is one of the KKT conditions. Yeah. You don't have to know all of the theory behind optimization. Yeah. So it's clear enough to just say that the penalty at the end has to be 0, right? That's really what the complementary slackness condition is. Yeah? At the end, the penalty you add, it has to be 0. Otherwise, you will not be solving the original problem, right? Okay, so that's that. So that means if this has to be 0, this product, right? So either alpha n star has to be 0, or this has to be 0, yeah? Has to be exactly equal to 1. So for each point, for each n, means for each data point, yeah, we should have either alpha n star equal to 0, or yn w transpose xn plus b exactly equal to 1. Yeah, the difference is 0. Right? It can be both as well, then can also satisfy. Yeah, but at least one of them has to be 0. Otherwise, your penalty will not be 0. Yeah. Okay. So everyone okay so far? But does this look familiar to you? Remember at the very beginning we said, what happens if this is actually equal to 1? This data point, what's special about a data point that has this one equal to 1? Yeah, sit right on the boundary of the margin, okay? So therefore, either the data point sits right on the boundary, or this one has to be 0. This alpha n has to be 0, okay? Yeah. So therefore, if at the end of your optimization, you found out that this optimal alpha n that you found is strictly greater than 0, yeah? In general, it's greater than or equal to 0, right? It's strictly 0, that means that it's not equal to 0, yeah? If you have a Lagrange model that's not equal to 0, then we must have the second condition must be true, yeah? This point must be sit on top of the boundary. So then yn times w transpose xn plus b